Chapter 20, Many Electron Atoms, Section 20.1, the Schrödinger Equation of the Helium Atom. The helium atom is considered one of the many electron atoms because a helium atom contains 2 electrons. So any atoms that contain 2 or more electrons are many electron atoms. A helium atom contains 1 nucleus with plus 2 charges and 2 electrons, each with a -1 charge. It is treated as a 3-particle system in quantum mechanics. Nucleus at the center surrounded by 2 different electrons. Their positions are specified by the R1 factor and R2 factor. Now let's look at the Schrödinger equation for the electrons in the helium atom. It's negative h bar squared over 2m sub e Laplacian plus negative h bar squared over 2me Laplacian for electron 2. The first 2 terms are the kinetic energy operators for the 2 electrons. Now we have the attraction felt by electron 1, the attraction felt by electron 2, and now finally the repulsion between the 2 electrons. E squared over 4 pi epsilon 0 R12. R12 is the distance between the 2 electrons. Now we have the Hamiltonian applied to the wave function of the 2 electrons. We get energy times the wave function of the 2 electrons. There is no way to solve this Schrödinger equation exactly. In general, there's no way to solve the Schrödinger equation for any system that contains 2 or more electrons. But still, we can get some approximate solutions. First, this psi, the wave function, can be written as psi of R1 and R2. Well, because we have 2 electrons with positions being specified by R1 and R2 vectors. And now this is the general form of the Laplacian, the sum of the 3 derivatives with respect to x, y, and z. We use this Laplacian for convenience because it's really easy for us to write out the kinetic energy operator for electron 1 and then for electron 2. R1 and R2 are the vectors pointing from the nucleus to the electrons. R12 is the distance between the 2 electrons. The mathematical form of R1, R2 are just this, the square root of x1 squared plus y1 squared plus z1 squared, where x1, y1, z1 are the Cartesian coordinates of electron 1 relative to the center, which is the nucleus. Same for R2. R12 is a bit complicated. It's the square root of over here. This is delta x squared, delta y squared, delta z squared. Delta is the difference between electron 1 and electron 2. Why don't we include the kinetic energy of the nucleus in the equation? Well, it's just 2 reasons. One, the kinetic energy of the nucleus is much smaller than the kinetic energy of the 2 electrons, and therefore it's often neglected. The second reason is if we do include the kinetic energy of the nucleus, that will make the Schrödinger equation more difficult to solve. Anyway, in the future, we will be able to recover the kinetic energy of the nucleus separately. There are 4 fundamental atomic units. The charge of an electron is 1. The mass of an electron is 1. H bar is 1. 1 over 4 pi epsilon is 1 in atomic units. So in atomic units, the Schrödinger equation for the helium atom can be really simplified to this. Kinetic energy operator for electron 1, kinetic energy operator for electron 2. This is the attraction felt by electron 1. This is the attraction felt by electron 2. And this is the repulsion between electron 1 and electron 2. Everything together, these 5 terms, is the Hamiltonian for the 2 electrons. We apply the Hamiltonian to the wave function of the 2 electrons, h psi equals E psi. The kinetic energy operator can also be expressed in spherical polar coordinates. Alright, because the Laplacian can be written in this form: 1 over r squared outside the square bracket. Inside there are three terms. The first term, delta over delta r times r squared delta over delta r. Second term, 1 over sine theta delta over delta theta, and then sine theta times delta over delta theta. The third term, 1 over sine theta squared, and then delta squared over delta phi squared. The derivation of this Laplacian in polar spherical coordinates can be found in Appendix P. It's very tedious. But now let's just assume, we can just simply use this for electron 1, we use this for electron 2. Even if we convert everything into polar spherical coordinates, we can still not be able to solve this Schrödinger equation. Because the Schrödinger equation now contains 6 coordinates, at least 6 coordinates: r1, theta 1, phi 1, r2, theta 2, phi 2. And also the distance between the two electrons, r1 and r2, can be really complex. Again, let's look at the Schrödinger equation for the helium atom in the atomic units. Kinetic energy of electron 1, negative 1/2 Laplacian for electron 1, and then kinetic energy operator for electron 2. Attraction felt by electron 1, attraction felt by electron 2, and then over here we have electron-electron repulsion. How do we solve this Schrödinger equation? We have to make approximations. Well, there are different levels of making approximations, so let's try the first level of approximation, which is so-called orbital approximation. We're going to say, well, let's try to separate the variables for the two electrons by doing this. The wave function of two electrons is equal to the product of the wave function of electron 1 times the wave function of electron 2. Alright, so it's the product of phi 1 and phi 2. So by looking at this, this psi squared is phi 1 squared times phi 2 squared, and psi squared is the probability density of the two electrons, is equal to the probability density of electron 1 times the probability density of electron 2. There's a underlying assumption over there when we do this. That's the probability of finding electron 1 at this position and the probability of finding electron 2 at this position are independent of each other. Alright, so two unrelated events for electron 1 and electron 2. But later we'll see, this is not a very good approximation because the probability of electron 1, probability of electron 2 are correlated. Now let's look at this approximation again. Phi 1 and phi 2 are one electron wave functions, also known as just atomic orbitals. The approximate solution to the Schrödinger equation is this: phi 1 is e to the power of negative zeta r1, phi 2 is e to the power of negative zeta r2, and then psi of the two electrons is just phi 1 times phi 2, which is e to the power of negative zeta r1 times e to the power of negative zeta r2. Zeta denotes the effective nuclear charge felt by the electron. How do we determine the value of zeta? We will first study two extreme cases to determine the range of zeta. So case 1, let's move electron 2 into the nucleus. And now you have just electron 1 outside the nucleus. Overall, the attraction it feels is only +1 charge, because when we have electron 2 located in the nucleus, now in the nucleus we have +2 and -1. Alright, together it's only +1, and then electron 1 outside the nucleus feels only +1 charge. Case 2, we move electron 2 infinitely away from the nucleus and from the electron 1. And in that case, well, the effective nuclear charge for electron 1 would be 2. So just imagine when we have a helium atom, it has 2 electrons. Now we send one of the 2 electrons to the moon. Alright, and then we have only a nucleus with +2 charge and 1 electron outside the nucleus on Earth. Alright, in that case, the effective nuclear charge is 2. So we consider two extreme cases, when R2 is 0, when R2 is infinity. The real case should be in between. Therefore, we say, well, the value of zeta, the value of the effective nuclear charge, should be between 1 and 2. Over here we have some values for the effective nuclear charge. Let's look at helium. The effective nuclear charge is indeed between 1 and 2. It's roughly 1.7. Well, you can say the 1s electrons in helium repel each other, so there's some electron shielding. And in this case, the electron shielding is approximately 0.3. So the effective nuclear charge is plus 2 minus 0.3. We get 1.7 approximately. If you look at lithium, well, there's 1s electrons, there's 2s electron. So for the 2s electron, you can say, well, approximately it feels electron shielding of 2. So the inner shell electrons, can effectively shield outer shell electrons. So the effective nuclear charge for lithium is roughly 1. So 3 minus 2 is roughly 1. Now let's look at the 1s electrons. Over here, this is 2.7. Why is that? Well, first, the 2s electron does not shield the inner shell electrons. So we only consider the electron shielding between the two 1s electrons. That's roughly 0.3. And then they both feel attraction from plus 3 protons in the nucleus. So plus 3 minus 0.3, I think we get 2.7. So we can qualitatively explain all those trends, all those numbers in this table, but let's focus on the helium atom. Again, it's the effective nuclear charge is roughly 1.7. So again, we have approximate solution to the Schrödinger equation for the electrons in the helium atom. It's the product of two wave functions, each for an electron. The wave function of R1 and R2 is the product of a wave function of R1 times the wave function of R2, and approximately it's going to be the product of two exponential functions, e to the power of negative zeta R1, e to the power of negative zeta R2. We consider two extreme cases in which the electron 2 is moved into the nucleus versus moving to the moon. So R2 can be 0, R2 can be infinity. In that case, we get zeta for electron 1. Alright, for case 1, zeta is 1. For case 2, zeta is 2. Therefore, in the real world, I think zeta is between 1 and 2. And again, zeta is the effective nuclear charge. We'll just use the experimental data for the first and second ionization energy of helium to determine the value of zeta. The total energy of the two electrons is simply the sum of the ionization energy of electron 1, the sum of and the ionization of ionization energy of removing the second electron. So it's negative 2.9 atomic unit. So what does this mean? It takes this much energy, 2.9 atomic unit, to remove both the electrons from the nucleus. And we use that state, separated electrons and nucleus as the zero reference. Alright, and then if we have a helium atom, it has a energy of negative 2.9 atomic unit. And now we're going to calculate the effective nuclear charge. The energy for this, if you have a y-electron system with a effective nuclear charge of zeta, the energy is negative zeta squared over 2. Now we have 2 of such electrons, so 2 times this energy is equal to negative 2.9. Alright, we solve this equation, we get zeta equals 1.7. So this value matches with the value we got from here, this table. The effective nuclear charge of helium is indeed roughly 1.7. So we're good, and the wave function of the two electrons can be written as e to the power of negative 1.7 R1 times e to the power of negative 1.7 R2. Alright, so again, this is just one of the approximations. Alright, and this wave function looks reasonable. Well, at least when you look at this wave function, you can see zeta is 1.7, and when zeta is 1.7, the energy is negative zeta squared over 2, right? And then we have two such electrons. The total energy is 2 times negative zeta squared over 2, and we do the calculation. It's roughly negative 2.9. And also we know it takes 2.9 atomic unit of energy to remove these two electrons. That means the total energy of these two electrons is indeed negative 2.9 in the helium atom, and everything seems to match. However, this wave function violates quantum mechanical postulate 6. In postulate 6, we have this: the wave functions of electrons must change sign under the exchange of two electrons. So if you exchange any two electrons, the sign of the wave function must change. So we have this mathematical form: the psi of R2 R1 should be negative psi of R1 R2. Alright, now let's look at this equation. So if we have this kind of equation, this equation is not anti-symmetric. When we exchange R1 and R2, so that means when we exchange this two, alright, we get this wave function. But this wave function is exactly the same as the original wave function. That means when we take this form for the wave function of the two electrons in the helium atom, it's a violation to the quantum mechanical postulate 6, because after we exchange R1 and R2, we get the same wave function. Supposedly the sign should change, but we didn't see any sign change of this wave function. And again, because after we exchange R1 and R2, we actually get the original wave function. We say this wave function is symmetric under the exchange of two electrons. Again, it's a violation of postulate 6. Postulate 6 says, well, the wave function must be anti-symmetric. That means the sign must change under the exchange of two electrons. So now, how do we kind of solve this problem? Well, we have to consider electron spin in the wave function of the helium atom to resolve this issue.